Okay, so is my mic working all right?
No,
Okay, I'll start off with a disclaimer. It seems like the presentation view is not working, probably an Ubuntu thingy. So just ignore the stuff around and focus on the presentation. And the typos are now going to get highlighted, so again, ignore. So my topic is going to be CKS enhancement in CloudStack. In general, we've made a lot of enhancement to the Kubernetes framework in CloudStack over this year. But before I get into that, a little bit something about me. I'm a software developer at ShapeBlue, a committer at CloudStack, and have been part of this this community since 2019, and loving every moment of it. So before I get into the details, the glossary bits: CAPI, Cluster API, CAPC, Cluster API for CloudStack. The CKS, which is the main focus point, is the CloudStack Kubernetes Service. CNI is our container network interface, which is used for which helps in defining how containers communicate with the networks. And the CSI driver, which is the container storage interface, which we will delve into a bit more detail today. So the evolution of Kubernetes in CloudStack. We started off back in 2016 with CCS as a standalone project and have come along a long way. Our big step was stage 4, where we entered the Kubernetes world officially with CAPC, the cluster API for CloudStack. And now we are on stage 5, where we've further improved CAPC, wherein we can view all of the resources in CloudStack. We've added a lot more features to provide a lot more flexibility for CKS, and we will have a small session of knowledge sharing for CSI driver, because we want the entire community to start for that particular project to gain some traction and for the community to use it. So the first bit, CAPC as an unmanaged CKS cluster. We always could deploy Kubernetes in CloudStack using Cluster API. However, there was no visibility on the CloudStack management UI. So with this feature now, with merely exporting this particular global set environment variable and following the same legacy way of initializing a CloudStack cluster using CAPC, it gets annotated with the specific parameter, and then you should be able to have view the entire cluster, the Kubernetes cluster deployed via CAPC on the management UI of CloudStack. So it seems simple, and it makes life much more simpler because you get a holistic view of all the resources being consumed. Going a bit more into the CloudStack side, a little bit of a precursor on what are the different nodes in Kubernetes. We have the control node, which basically, as we all know, does the overall state management of Kubernetes cluster. Worker nodes, which are mainly responsible for deploying your workloads, and the HCD nodes, which are the distributed key value storage and store the state of the cluster. Now, based on the different responsibilities, we notice that there are different recommended specification in terms of CPU and RAM and storage. So this comes, you see there implicitly is a need for us to be able to deploy different node types in CloudStack with CKS with different service offerings. So today, yes, it's a little slow as well. So today we see that the CKS form is now evolved to have now service offerings for different worker node types. This lets the end users to define, to decide what kind of operations and what responsibilities different worker nodes are going to be performing, and use the appropriate service offering for different node types. The next one is the choice of node templates. We started off with using Core OS, that evolved into using system VM templates, but it was very restricted to deploying CKS clusters with only system VM template up until with this feature now, you can use custom templates for deploying CKS clusters. What purpose does it serve is you can pre-configure your templates with different resource allocations, software stacks, so that once the cluster comes up, all the necessary applications and software is available to the end users, and the Kubernetes cluster comes up and running. How did we make this possible? So just as we have a project or the script for building templates for system VMs and for built-in templates, we've extended that to now help build Ubuntu-based templates, but this, based on community traction, we can extend to support different other operating systems as well. So the first bit is all the required dependencies are installed, which are required for CKS, followed by creation of the cloud user, because all of the interactions in CKS happens with cloud user, which needs to have administrative permissions. Then the CKS directory, a required directory is created in the template or the image. Finally, the cloud user needs to be injected with the management server's SSH key. And then the registration of the CKS template. We will see how this is done. Yeah. So for this template to be considered usable for CKS, at the time of registration, the CKS flag needs to be listed, needs to be checked. Only when that is checked will it be visible for selection at the time of creation of CKS clusters. So here we see that now you can choose any template for deploying different node types, thus bringing in the whole concept of heterogeneous clusters. The next bit is importing external nodes into CloudStack. A little bit of highlight on the word node. We didn't say VM as such, because now we can also import bare metal nodes. To know further about this, please do attend a session by Alex and Hari tomorrow. So how has this been enabled? We have the node validation phase. The node validation checks if all the necessary packages have been installed. Then firewall and DNAT rules are installed for secure communication. Further, the specific worker node that needs to be added will be rebooted with the necessary user data, and the ISO is attached to it. The ISO being the CKS ISO that has all of the necessary binaries required for the CKS cluster to come up. So delving into details of what are those node requirements, it needs to be the said external node needs to be deployed with a template that has been registered as a CKS template, and needs to be deployed with its default NIC in the CKS cluster network. And also, this particular node shouldn't be part of any other Kubernetes cluster. So just to give an overview of how it looks on the UI, on the left side, we have the blue button, which is to add an external node into CloudStack. On this screen is the pop-up window that it opens. Here we see that there is an option for you to use the virtual router to host your or to serve your CKS ISO, and this has been done specifically bearing in mind that we now support bare metal nodes. Okay, moving on. Since we add support for addition of external nodes, there's obviously support for removal of external nodes. What it does is as simple as it first drains the node on the control node, then goes on to the worker node and resets the worker node. Once the worker node is reset, you'll see that the state of the worker node is gone into schedule disabled. So no new workloads will be scheduled on the specific node. Then you do a delete operation. So when you do kubectl get nodes, you will no longer see that specific externally added node anymore part of the Kubernetes cluster. And finally, all of the required firewall rules and port forwarding rules are removed. Next bit, important for production environments. We have this concept of unstacked HCD, which is always considered that it is better to have the HCD cluster outside the control plane solely for security reasons primarily, so that it is away from attacks. Also, it is independent of the CKS or Kubernetes cluster for scalability purposes. So it enhances flexibility, scalability, and reliability in entirety. How has this been enabled? All the newer CKS ISOs are bundled, have been bundled with the HCD binaries. When at the time of creation of the CKS cluster, if the number of HCD nodes has been set to a value greater than 1, greater than 0, the HCD service is started. And currently, just as we have the destination ports for SSHing into each of the worker nodes or control nodes set to 2222 and so on, for entering into the HCD nodes, currently there's a global setting which defaults to 50,000. The port forwarding rule that is added is from 50,000 onwards. This can be configured via this global setting. A comparative view. On the top, you see a cluster that is deployed without HCD. So you notice there is no HCD pod created. However, on the UI, you notice there is an HCD node. At the bottom, you notice that it is a legacy CKS deployment with an HCD cluster. Next bit is manual upgrades of CKS nodes. Since we've added support for external nodes being added into CKS, it is a common assumption that there could be certain specific software stacks included as part of this node that needs to be manually managed and cannot be upgraded in the normal way that CKS upgrades the CKS clusters. So in order to support that, at the time of addition of this external node into the CKS cluster, one needs to mark those nodes for manual upgrades. So when an upgrade is performed, those specific nodes are not considered for the upgrade process. And in order to aid in knowing exactly which Kubernetes version is running on specific nodes, we have the node version field included as part of the Kubernetes response. Next bit is CNI as a first-class citizen. Now, in 420, we've added support for Calico and the Cilium CNI plugins. However, these do not have the support of configuring them at runtime. So if you want to pass some user data and configure the modify or substitute some values at runtime for the CNI configuration, you can use CNI, the CNI feature, which basically falls back on user data as such in the background. How does this work is on the left-hand side, we see register CNI form where we've added the CNI configuration that takes the peer IP address and the peer AS number as inputs. Now, when this CNI is associated at the time of CKS deployment to a cluster, we can pass the required IP address and AS numbers at runtime. The next bit is dedication of CKS nodes on specific hosts of ACS CKS clusters. Historically, we've always had support of dedicating hosts to a specific domain and account, but CKS did not adhere to this policy, basically that when you deploy a CKS cluster in that specific domain and account, the CKS nodes would end up going on any available host and not those that are dedicated to the account and domain. But with this feature, it does first check if that specific domain or account has the necessary resources or hosts for deploying the cluster. And if it doesn't, then moves out and deploys it on any available host. The purpose of this is better resource management and better resource allocation. So that was a bit on all of the enhancements we've done so far on the CKS front. Going into the CloudStack CSI driver, we've had our community members from Apalia and Lee's Web do a lot of work on the CloudStack CSI driver so far. However, it hasn't reached the community and hasn't received as much love and affection as it should have. So we thought we'll take an opportunity to bring it into the overall Apache CloudStack flagship. So this is a small attempt. So I first forked it into the Shablue repo as of now, and we hope to contribute this to the Apache Foundation soon. So the idea of the CSI driver, it's basically a standard that is used for providing arbitrary block and file storage system for containerized environments on container orchestration systems. And it provides a way to seamlessly integrate Kubernetes with any storage provider, in this case CloudStack, to make use of all of the storage capabilities it offers. So just to get into basics of volumes on Kubernetes, they are basically file systems that enable sharing of data or information between containers in a pod and enable inter-container communication. They allow also or enable stateful applications by providing persistent storage. And that brings into, so that brings us to talk about the different types of volumes that we have. We have ephemeral volumes that are mainly suited for more data sensitive operations wherein we do not need the data to be persisted. So we generally go for ephemeral volumes. But we need also those type of volumes wherein you want the data to be persisted beyond the life cycle of a pod that continues to live despite the pod crashing. So for which we have persistent volumes in Kubernetes. To provision them, there are two ways of provisioning volumes in Kubernetes, which is static and dynamic. For dynamic provisioning, you do not really need to specify the amount of disks that is the volume that is required to be used by the deployment need not be created. It is created at the time of deployment of the application. So let's just get into some basic examples. One could create a pod. In the pod spec, one could specify the volume specification that directly points to the, here in this case, it's pointing to a Google Cloud persistent disk. However, this kind of volume definition is not really scalable in nature, because if you move this to a non-Google Cloud environment, this pod spec needs to be modified. So in order to make it more generic, we had in Kubernetes persistent volumes and persistent volume claims, wherein persistent volumes are created by the administrator, which basically indicates what volume is available for amount of storage available in the cluster. The persistent volume claim is created by the user that specifies how much storage the specific workload requires and what access mode for this storage. And then there's the claim binding, wherein the persistent volume claim binds to the persistent volume that has been created by the administrator and finally made usable available to the pod for usage. But that, as we saw earlier, since we mentioned that specifying the specific cloud-specific volume as part of the volume spec in the pod is not scalable in nature. Using persistent volumes claims becomes a more scalable approach of using volumes in Kubernetes. So thus comes into picture dynamic provisioning. In dynamic provisioning as such, you do not need to create persistent volumes. They get created at the time of the workload deployment. But here, there's a new concept called storage class. Storage class basically defines the volume plugin that is going to be used to facilitate and provide the storage for your containerized workloads. And you specify the dynamic parameters that are required for provisioning these volumes. Now, for CloudStack, as you see here, the storage provisioner is going to be, it points to CloudStack. This gets added at runtime. When the CSI driver receives a request for creation of a persistent volume claim, it first checks its in-tree storage provisioners if they can provide this particular volume, or if the volume already exists. If it does not find any provisioner that can provide it, it checks for the storage class and adds the specific provider of the storage class as an annotation to the persistent volume claim request, and then that request is sent to the pointed volume plugin, and hence the volume gets created on, in this case, CloudStack. So this is a diagrammatic representation of what I just said. So let's move ahead. Speaking of CSI specifications, highlighting a bit on this because this gives an overview of how even CloudStack CSI driver has been implemented. There are ideally three services that are defined. The controller service basically manages all of the volume lifecycle operations like the create and delete operations. And the CSI driver as such, as we said, it's a standard. It defines all of the capabilities and all of the RPCs that need to be defined mandatorily or optionally by any CSI plugin. And all of those details can be got by the controller get capabilities method or RPC call. Similarly, for node services, they specifically handle all of the volume operations on any worker on any node, such as mounting and unmounting of volumes on the nodes. These are generally deployed as daemon sets, and similar to controller service, the node service capabilities can be retrieved using the node get capabilities RPC. So in general, if you have to take a look at the overview of the various events that take place is when a PVC is created is first to get a create volume request. That create volume request is sent to the service provider or storage provider, here being CloudStack, wherein the volume gets created on CloudStack. Then the controller publish volume event is triggered. This attaches the volume to the node. Once the volume is available on the node stage volume event enables the volume to get mounted on a specific staging path, thus making it available to all of the pods in a node. And once the node publish volume event gets triggered, the volume is mounted onto the specific workload that is requesting for the volume. Okay. Hopefully this works. Just a second. Okay, so this is a demo of the CSI driver because this is, we're running short of time. So we start off with let's do something here. Let's skip ahead of all of this. Just logging all of the sidecar containers. So this is the first step of it is creation of storage class. Storage class is where you define the volume plugin. And here is where you have to specify the custom disk offering. Currently, we only support custom disk offerings. So here we go on to create the storage class, a pod, and the PVC. I think it's hung. It's stuck. As you notice that after we create the pod and the PVC, a lot of the events that we spoke about earlier gets triggered. You see a volume attachment operation being or an event being triggered, which sends this request to CloudStack, thus creating the volume on CloudStack, and we see the pod up and running, which indicates that everything is successfully created on the CloudStack end. And notice the, sorry, there's another view. Yeah, the PVC created here on CloudStack, which is the volume request that was made from the CSI driver. This is, sorry about the, let's see it. Okay, so let's go into the CKS enhancement. Here you notice that we already have a CKS deployment. There's one control node, one worker node, one HCD node. Each of them deployed with a different service offering and a different template, truly heterogeneous in nature. I'm just going through to show the different template and offering used. This template has been marked true for CKS usage. So only this specific template or any template marked with that flag will be listed for CKS deployment. Here we have two external nodes that have been deployed in the CKS network. For it to be added into the cluster, we need to first place the SSH key, as we mentioned earlier. So I'll be placing the management server's SSH key into the cloud user's authorized keys file. Okay, so I just skipped the whole thing. I've done the add node to the cluster because we're running out of time. This will begin the process of, as we saw in the whole workflow, it will reboot the node and inject the user data that is required for it to be configured as a worker node now. All the port forward and firewall rules necessary are attached, are created, and the ISO gets attached at this phase. So As you see at this point, the node has been added, but it's not yet ready. And now it's added into the cluster. So this should, this basically got added to the cluster. Now this is in a demonstration of upgrading, manual upgrade. At this phase, we have an external node that has been added with manual upgrade checked. So we should see that the node, after completion of the upgrade of the cluster, so here we see the node versions for the control and worker node is 127.8, but the external node, which was marked from manual upgrade, remains 1.27.3. And finally, external node removal. So at this point, you have external node present and then not. So yeah, it's a bit of a mess up, but hopefully.
Thank you very much, Poro. Unfortunately, we don't have time for questions, so feel free to catch Poro at our booth or